All right, this is going to look at another really common and fun sound phenomenon that you've all experienced, even though if you didn't know what it was called, known as the Doppler effect. So the Doppler effect is that experience you may have had where you are standing on a street corner and a car goes zooming by and you sort of hear this kind of a sound. That change in pitch because something is moving, right? That's really what we refer to as the Doppler effect. And we're going to look at what gives rise to the Doppler effect in this mini lecture, as well as how do we mathematically represent it. So it involves the perception of sound with motion. The perception of sound with motion. And the motion piece can be a combination of, well, the sound is being generated by some source. We're going to use an S to designate the source. The sound is being perceived by some observer, so we're going to use an O to designate the observer. And when motion comes into play, the source could be moving, the observer could be moving, or they could both be moving. So how does the sound perception, what the observer experiences, change when the source is moving, when the observer is moving, and then it kind of in general when they're both moving? So we're going to have to define some variables so that we know what we're referring to. And when we talk about perception of sound, we talk about pitch in the physiology system. And so pitch, as you've learned when we first introduced sound, is related to frequency. So we're going to use frequency as our base sort of descriptor of sound. And we have to, like I said, define a few things. So the frequency of the source, so the thing actually making the sound, you could call that the true frequency. We're going to define it as the frequency of the source. It's going to be F sub S. So this is the frequency of the source. What we hear, what we perceive, actually in this case, it's physiologically the same thing, unlike when we talk about vision, and the perception is slightly different than the physics. Here is what actually reaches our ears and then gives rise to the information our brain processes. We're going to use that lowercase o like I talked about. So this is the frequency of the observer. And this is actually what enters the ear. And then, of course, what we perceive. Now, I said some things can be moving and some can't be and may not be moving. So the velocity is going to, or the speed of the source is going to be denoted as V sub S. And the speed of the observer is going to be denoted as V sub O. All right, so here are the variables that we need to talk about. Now let's start with the case that we have a moving source. So what might that look like? Well, let's imagine that you have a boat, and I use a boat because I can draw those better than a car. You have a boat and you're kind of standing here on the shoreline. And that boat is moving towards you. Now, if the boat was stationary and the blaring its horn, it would send out a wave pulse every time the horn blares at a certain frequency. So as that wavefront moves towards you, it's moving at a certain frequency. Okay? The distance between wavefronts stays the same because the speed stays the same because it's moving through air, and that's what dictates its speed. And it hits your ear, and a wavefront hits your ear at a very specific amount of time. The frequency of the source, if the object is not moving, the frequency of the source and the frequency that the observer experiences is the same. Now let's take that boat and we're going to start moving it towards the observer. So here's where my drawing is going to start to have a little bit of issues. So here's my boat, and now it's actually moving. I'll move that arrow down closer to here. So it's actually moving. It sends out a wavefront, and this wavefront is going to travel at a certain speed to hit my ear. But as it moves forward, this one moves down. As it moves forward, it sends out its next wavefront. So the next wavefront ends up being sent out closer to the wave in front of it. So the next wave why is it sent closer? Well, now the ship, instead of being here, it's here. So as it sends out that next wave, it's already moved a little forward where the wave would have moved, and it's sent that wave out a little bit closer. And then it continues to move, and so it's getting closer to the next wave, and it sends that wave out a little bit closer. When those waves that are being sent out closer and closer to each other hit my ear, I get waves hitting my ear at a more frequent rate. I increase the frequency, or the frequency of the observer is increased relative to the frequency of the source. The source is still sending it out at the same rate, but because I'm moving towards that wave front, I've shortened the distance between them. So, such that the frequency of the observer is greater than the frequency of the source. That happens with a moving source. The frequency of the observer is greater than the frequency of the source if it's moving towards the observer. Well, what if it's moving away from the observer? What if now I send that wave front towards you and then I skedaddle in this direction and send out another wave front? Now I'm further apart than I was. I've moved away from the wave front traveling towards you before I sent the next one, and my wave fronts then that ultimately hit you are further apart. Then it's going to decrease the frequency that the observer experiences. So if the source is moving away from the observer, then the frequency the observer experiences is less. So not only do we have to understand how fast the source is moving, but we have to understand if it's moving towards the observer or away from the observer, such that the relationships developed give rise to this conceptual idea that we just outlined. As the source moves towards the observer, I start to compress those waves closer together, and those waves hit my ear in less time between them than if the object was stationary, the source was stationary. And conversely, if I'm moving away, I send one out, I run away from it, I send out the next one. The frequency I observe as an observer is more spread out, thereby decreased in my inner ear. And so this all gives rise to an equation where the frequency of the observer for a moving source the frequency of the observer is equal to, it's related to the frequency of the source, times 1 over 1 minus the velocity of the source divided by the velocity of sound itself in traveling in the air, where V sub s is V sub source. Now, does this work mathematically? It does. But if the velocity of the source ratio between the velocity of the source, so this is moving, this is moving towards, this is really plus or minus, where the minus is moving towards and the plus is moving away. All right, the velocity of sound, the velocity of the source is always going to be less than the velocity of sound. All right, we're going to talk about velocities of objects being less. When it's more, we get a sonic boom. We're not going to relate to that right now, but you can imagine that the source is less than that 343 meters per second. So the velocity of the source is less than the velocity of the sound. So this ratio is always less than 1. 1 minus a ratio less than 1. 1 minus gives me a little less than 1. Okay? If I'm a little less than 1 in the denominator, 1 divided by a number a little bit less than 1 increases my velocity of the source. So I get an observed frequency. I get an observed frequency that's larger than the source frequency. 1 divided by a small number is a number greater than 1. A number greater than 1 times the frequency of the source gives me a greater than observation. If I'm moving away, I add the ratio of the source to the ratio of the sound. That's 1 plus the velocity of the source. I get divided by the velocity of the sound. I get a number a little bit bigger than 1. 1 divided by a number a little bit bigger than 1 is a number less than 1. And if I multiply that by the velocity of the source, I get a smaller number, thereby confirming our generic relationship. Okay, so this is the relationship for a moving source. Of course, I don't ever think anyone should memorize equations, but you do need to understand where they came from, and it's really important that you understand whether you add or subtract the ratio of the speeds of the two sounds. Okay, well, that's a moving source. What if I have a moving observer? I actually think this one's a little bit easier to conceptualize. Not that the moving source was that difficult. Cumbersome, they're cumbersome, but what if I have a moving observer? Well, now imagine my stool with my speaker on it. And you're the one that's walking towards the speaker. When nothing is happening, again, remember this speaker is just putting out wavefronts, evenly spaced. If you're walking towards the speaker, well, then you're running into those wavefronts sooner than you were supposed to, right? If you're just standing there, you're running into them sooner than you're supposed to. So the frequency you observe must be greater than the frequency of the source if you are walking towards and hitting those wavefronts quicker. As you're walking away from the source, so if instead of towards the source, you're walking away from the source, then you're kind of like running away from those wavefronts. So the distance between when you get them, when you experience them hitting your inner ear, goes up. So less frequency, so the frequency of the observer is less than the frequency of the source. Right, so it's just the opposite of the observer. How do we represent that mathematically? Well, we represent that mathematically by the frequency the observer experiences is equal to the frequency of the source, so it's always related to the source, times 1 plus or minus the velocity of the observer divided by the speed. I should say speed, not velocity, the speed of sound. All right, does this work? And what does the plus or minus mean? Well, when I am running towards, I use the plus. Does that work? As I'm going towards the observer, if I add the ratio of the observer to the speed of sound, I get a number a little bit bigger than 1. A number a little bit bigger than 1 times the frequency of the source gives me a larger observed frequency. Works. If I'm running away from the source, then I subtract a little bit the ratio of the speeds. Number less than 1 times the frequency of the source, I get a little bit smaller number. And so the observed frequency mathematically matches what I deduced conceptually. Again, I don't believe in memorizing equations, so hopefully if you're in my course, you don't have to. It's provided for you. But if you're not in my course, use the conceptual ideas, remembering that the contribution of the source moving is in the denominator, the contribution of the observer moving is in the numerator, and then thinking about how those plus and minuses relate to what we did conceptually will help you derive these equations if necessary. Now, what happens if both are moving? If the observer and the source is moving? We're not going to go through the different scenarios: observer moving away, source moving towards, observer moving towards, source moving away, both moving towards each other, both moving away from each other, although you could. And I encourage you to think conceptually about how that would impact the sound. But I'll just tell you mathematically how that works. And it's going to make some sense, because if one of them is not moving, that piece sort of just falls out by multiplication of 1, falls out of the overall equation. So just to make sure I don't mess things up, the general equation for the Doppler effect, the general Doppler equation is given by the force of the observer is some relative amount for the force of the source. So 1 plus or minus the velocity of the observer over the velocity of the source, divided by 1 minus or plus, and I'm doing that intentionally, the velocity of the source over sound. The velocity of sound, not the velocity of the source up there. All right, so it's just kind of combining these two equations together, where on the top, the plus means towards. The observer is moving towards the source, where the minus means away. And on the bottom, the minus means towards, so I keep those consistent for you. And the positive means away. So it's just combining these two relationships. I will give you all three if you're in my class. If you're not in my class and you have to memorize that, I might choose to memorize the top one, understanding those relationships. Does this work if a source isn't moving or an observer isn't moving? Yeah, it just gives rise to these two. If the source isn't moving, this ratio goes to nothing. And I'm dividing the top by 1, the moving observer by 1. If the observer isn't moving, this ratio goes to 0. And I'm back to my equation that represents just the source moving. So the generic equation works perfectly in our specific examples. I think these help you delineate them a little bit better, so I wanted to share them with you. Doppler effect is super fun. Super fun. We hear it a lot. Should be consistent as we hear something going towards us or away from us. The next time you observe the Doppler effect in your real life, are you hearing the frequency get lower when it should get lower and higher pitch when it should get higher pitch, based on your newfound understanding of the physical and mathematical relationship? All right, good job.